If nobody claims on, then I will take this. Can I write here? Yes, maybe. Someone put
Okay. First wash it and then you can.
Okay. Yes.
Okay, so I wanted to say a few more words about differential equations with continuous right-hand side. It was f of x, y. And we solved the initial value problem, y at the point x0 equals y0. No, last time I showed how using non-standard methods prove existence of solution of this equation, where f is a continuous function in some domain G, just continuous. In this situation, the solution can be non-unique. Yeah, no, the most popular example is f of xy equals 2 square root of model y. Yeah. So if you solve this equation and let us take y of 0 is 0. Yeah. So there is one obvious solution, y1 of x equals 0. If you substitute it here, you see 0 equals 0. So it is one solution. But there is other solution, y2 of x equals x squared. So it also satisfies both equation and initial condition. And we can find infinitely many solutions. Y3 of x equal, say, 0, x less or equal than x0, and x minus x0 squared, x more x0. Yeah? For any x0, we have this solution. Here it is 0, and here it is just a square function. So we have this family of solutions. No, that's it. No, I would say that this example maybe is not typical. Here equation behaves too fine, too smooth. In general, equation can have non-unique solution for given f x y for any x0 and y0. So for any initial point in our domain G, we have more than one solution. Now, if you have two different solutions, then you have infinitely many solutions. So it is highly non-unique. And but my way of proof, it was, no, I would say, constructive, if it can be used for the proofs using non-standard methods. Yes, it produces just one solution. Yeah, so not infinitely many solutions, but just one of them. Yeah. So how it can be? Is not here some contradiction? No, in fact, no, it is no contradiction, because in fact we had here a lot of parameters. Namely, we fixed some non-standard model. So non-standard model in our construction of non-standard analysis includes index set I, includes some ultrafilter on this index set, and there also was the step size, which was also some infinitesimal number, and much could depend on this number. So we had a lot of parameters. Yeah? So what we really constructed was a family of solutions which is sort of parameterized by these parameters, non-standard model and this infinitesimal. And this is not exhaustive. I think that we can propose different ways to construct solutions and have different different family. But anyway, what we found here is a sort of parameterization of solutions of this highly non-unique family by non-standard models. What is more important, and this is a real problem, is another thing. If you have not a unique solution, but a family of solutions, usually it is infinite or even infinite dimensional family, we have to, if we want to say something beyond that it is non-unique, we should introduce some structure. And the nature structure for this is a measure. Yes? So if the solution is non-unique, maybe we can introduce a measure and regard it as, say, random solution. As far as I know, it is not done. So this is still a subject of research. Next thing is that the following. Here, y can be multi-dimensional. It is not only a point on the line, it can be a point in some space, on some manifold. Yeah? And especially interesting is if y is a point in three-dimensional space, and f is velocity of some fluid. Yes, how to imagine vector field in three-dimensional space? It is a field of fluid velocity. And if you have, say, really turbulent motion of this fluid, then the velocity field for turbulent flow, velocity field, no, here it is F. Is a Herder class function. Yes, and here alpha is approximately equal 1/3. This is famous Kolmogorov's 1/3. Yes, you know what is Herder class. Yeah, so the difference between f of x and f of y is estimated through x minus y distance to the power alpha. So alpha is about 1/3, no, 1/3 minus epsilon. And so it is far from Lipschitz, and so typical trajectories are non-unique at every point. Yes, and here this problem of studying solutions and of establishing some measure in the space of solution is a very physical problem. The problem of turbulent mixing of admixture, say, of some paint. So we add some paint, and then this paint is being mixed by the turbulent flow. So it is one of the main problems of turbulent studies. And so again, we are here. There are some physical activity around this. No, but I'm not sure that the results are correct, I would say. One more comment to this problem is the following. So consider this problem. Suppose here we have some data. So we start from data. Data is positive. Okay? Then let us consider the approximate method which was used to solve this problem. So delta equals y0. We chose the point x0 equals 0, say x1 equals, say, 1 divided by n, xn equals 1, yes, and we constructed the approximate solution by the following formula. So y0 equals delta, y1 equals y0 plus 1 over n times f of x0 y0, and so on. Yk plus 1 equals yk plus 1 over n times f xk yk, and so on. Where f is exactly what is written here. Now, if we fix n, then f, I say, yn is depends on, after all, if you start from delta, then yn depends on delta. Yes, because if you substitute here, every next y, y1, y2, and so on is determined from the previous by this explicit formula, and everything is defined by this first term delta. Yn is a function on delta. Now what we can say, yn of 0 is 0. Yeah? And what else? We can see that this function is monotonically growing. Yeah? It is continuous. Yeah? So we can say, so yn, say, of some delta, let's call delta n, equals 1. Yeah? You can always find some delta, delta equals delta n, where delta n positive. Yeah? This function as a function of delta is continuous, so we can find delta such that yn at delta is yn at point 1 is arbitrary number between 0 and between 0 and 1. Yes, in this case. No, okay. And now what happens if you pass to non-standard situation? So n now belongs to, let us write start n minus n. Yeah, no, instead of writing this all the time, let me call this inf. Inf is a set of infinite numbers, infinite integer numbers. So if n is in, yes, then you have the function yn of delta. It is the function, so it depends on n and on delta, from star n times star r to star r. So it is it maps these sets, yes, and by let me write the formula which describes the properties of this function yn as a function of delta. For any n, for any a, say between 0 and 1, there exists delta positive delta such that yn of delta equals a. Yeah. So for any positive n, for any a, there exists delta such that yn, where yn is defined by these formulas. And now by transfer, we have the following formula in the non-standard universe. For any n in star n, for any a in star 0, 1, there exists delta in star r plus such that yn of delta equals a. Yeah? So what does it mean? One moment. And one thing which we proved last time, that if you consider the function yn of delta, let us yn of x equals yk of if x equals k divided by n, and I will say linear interpolation otherwise. The last time it was a formula, so we have this discrete points. It is discrete, so it is xk, it is yk. And now we interpolate the function linearly between them. So we have this piecewise linear function, which interpolates between these values. So it is yn of x. And now you consider the function y of x equal standard part of yn of x. Yes, where n is infinite number. So it is standard part of a function, this function of two variables, n and x. Yes, and here we have the argument, we have this function, and we have to repeat this construction of standard part of anything. So for any non-standard x, which is say between 0 and 1, we find corresponding non-standard y, and then take the pair standard part of x and standard part of yn of x. Yes, and this pair is a point of the function standard part of all these. And we have that last time I proved that this is solution of equation. So if it is solution of equation, then what we have here it is point 1, it is A, and here solution is unique. So here solution is given by some quadratic function which for x equals 1, this function is A, so for some x0 it is 0, and then it goes like 0. Yeah? So this is the standard solution. But here we found non-standard solution. We found non-standard solution, this y capital N. It is a non-standard solution. So what can we say about this non-standard solution? Here the standard part is 0. So solution takes infinitesimal values, infinitesimally small values. Yeah? And so we have a function. Here it is equal to delta. Delta is also infinitesimal. But here delta is in non-standard R plus, so it can be infinitesimal. Yeah. So we have an interesting function which is infinitesimal here, and then it becomes positive, not infinitesimal. Yes? And this function is at the same time defined by this rule, and so it is internal function. So it is a legal function which can be used in non-standard setup. Yeah. So to some extent, this problem of non-uniqueness is in fact solved. So this non-uniqueness is encoded in this delta. Yeah. So it says that this zero solution is in the sense non-stable. So if you start not from 0 but from infinitesimally small positive, then a solution will sometime follow this infinitesimally close and then jump to finite values. Okay, so this is about equation. No, I think this topic is much larger than what I told you today, but mostly it is unexplored. Okay. And now I wanted to move to a topic which lies near differential equation, but okay, dynamics. So let me consider the following setup. Suppose we have E Euclidean space. Now it can be finite or infinite dimensional. And we have some set omega. Closed subset. And we study the motion of a material point on omega. So the point is, material point is forced to remain on this set omega. It moves without friction, at least without explicit friction, by inertia, and all this in some Euclidean space. It is not the most general setup for dynamics. Of course, we have no potential energy, no, we have no friction, as I said. So it is some idealized situation, and the most important model where we meet this situation is the motion of fluid, ideal incompressible fluid, inside some domain, some vessel. Yeah, so if you have a pool of water and some flows and vortices in it, then it is described by this situation. Now we can consider more primitive models of the same. I will show you a little later. So the question is how to describe it. So we have here the problem. What is the law of nature which describes the motion of such material system? The problem is not so easy. If you consider, say, smooth curve in the plane, it is like the simplest situation, then we can propose the following procedure, which leads to a description of it. Let us take some initial moment, point x0, and let us consider the initial velocity, u0. And let us set some time step tau. And now we define the following point. At the point y1 equals x0 plus u plus tau times u0. So it is the displacement of the particle if there were no this curve. Now, so we have the point y1. Now we define the point x1. Let me call this projection of y1 on our curve, let's curve gamma. What is projection? Is the closest point, nearest point. So this point is x1. So we have x0 and x1. Now we proceed as follows. we have 2 points, so the approximate velocity is difference divided by tau. So we write y2 equals x1 plus x1 minus x0. Yeah? It is y2. x2 equals projection on gamma of y2. The closest point. No, here I take 2 large steps, so it doesn't look very close. No, similarly, you continue yk plus 1 equals xk plus xk minus xk minus 1. Yeah, so you have 2 points xk plus 1, xk minus 1 xk. I continue this way, it is yk plus 1, and then xk plus 1 equals projection on gamma of yk plus 1. So it is xk plus 1. So what we anticipate in this situation? How will the point move along a smooth curve? No, if there is no friction, and then the only reasonable hypothesis is that the curve will move with constant speed, because nothing keeps it from constant speed. Nothing forces it to change the speed. And if you analyze this process, and very simply you will see that in fact when tau goes to 0, then this chain of points on the curve will become asymptotically equidistant. So the distance between them will become very close to one another. Yes? So this process really gives us good approximation, no, maybe not very well converging, but gives some reasonable approximation to this anticipated trajectory. Now, what is interesting here, what happens if this set omega is not a smooth curve, but something non-smooth? Yes, for smooth things, mechanics has a good apparatus to describe it, this motion. But what happens if it is non-smooth? No, for example, suppose that our omega is just segment from 0 to 1, for example. This is our omega. So when a point moves along this line, here it moves with constant speed. But what happens when it hits the end? What happens? Will it bounce back? Or will it stop? Will it bounce back with different speed? How to describe it? If you have a point which is moving and hitting the wall, the particle moves and hits the wall, what will happen with this particle? No, we think that it will bounce back by the law, but why? Maybe not. What will happen if we have here a corner and this particle gets it right in this corner? Yeah. What happens if we have, like here, two walls and ceiling, and my point gets exactly into this triple corner? How it will move further? You can believe me that I really took a tennis ball and tried to hit exactly that point once, and saw what will happen. And imagine that we have such a non-regular situation that all this omega is made out of these corners. So not just isolated points, but typical points are like this corner. How it will move? Yes. If not you but me return to description of the fluid, then we have exactly this situation, that fluid flow is in fact the motion of a point in infinite dimensional space along infinite dimensional set omega, and this omega is even highly non-smooth, much less smooth than this system. Yeah? And what is the true description of the fluid flow in this situation along this set is still unknown. There is no good definition of how the fluid does move. What we call the equation of motion relates to some very restricted and I think very degenerate motions. Yes, so it is one of the basic problems of all our science. Okay, but let us look at this process. This process appears to give us some hope. So again, we start from 2 points, x0, x1 in omega, 2 initial points. Then you write this chain of points. You take 2 equals, say, 1 over n. So we consider the motion of the point on the segment t from 0 to 1. And we write x y2 equals x1 plus x1 minus x0. x2 is projection on omega of y2, and so on. Y and k plus 1 equals xk plus xk minus 1. Xk plus 1 projection on omega of yk plus 1, and so on. And so you have the chain x0, x1, xn. Here comes one thing immediately. This first step is clear. What about this step? Here we have project. What's projection? The closest point. But if the closest point can be non-unique. Yes. So if it is non-unique, no, typically it will be non-unique more or less at every step. So we have highly non-unique trajectory. And this choice is can lead to something which is, I would say, leads astray. Yeah? The man who introduced this process was Jan Brenier, very good French mathematician. He already tried to apply it to the motion of the fluid. But it turned out that this process, in that case, was so complicated and maybe so unique that he only studied just one step here, just how to find this projection. And this already led him to some very beautiful and powerful theory, but did not help with fluid dynamics. And why it all happened? Because this is non-unique, and when it is unique when the set omega is convex. Yeah? So let us assume that omega is convex set. That omega is convex. It is a restriction, but there exist interesting systems with omega convex, so it is not empty situation. If omega is convex, then by sure the closest point is unique, because if this point x, and we have here 2 points y and z, and this is omega, which are closest, so the distance to y and distance to z are equal, then we can take this segment between y and z. It is completely inside omega because omega is convex, and take the midpoint, and the distance to midpoint is smaller. Yeah. So this means that for convex omega, this projection on omega of y is uniquely defined. Here is another fine thing before we move further. Let us consider one step of this construction. This is the point, this is omega, this is a point xk minus 1, this is xk, and now we continue it further. And this is the point yk plus 1, xk plus 1. Now, what I claim that the length of the segment between xk and xk plus 1, xk plus 1 minus xk, is always less, no, or equal than x k minus xk minus 1. No, why? It is because this triangle xk yk plus 1 xk plus 1 triangle xk yk plus 1 xk plus 1 the angle xk plus 1, this angle, xk plus 1, yk plus 1, xk plus 1, yk plus 1 is obtuse. All right. So this angle cannot be acute. No, in fact, if it is acute, if you have this situation, then we can, all this segment lies inside omega, so we drop this perpendicular, and this distance will be smaller than this. Yes? So it is xk yk plus 1 xk plus 1. Yk plus 1 xk plus 1 will be not the shortest segment from yk plus 1 to some point of omega. This is closer. Yes, so it is, this means that it is not projection. So this means that this is obtuse. If this angle is obtuse, then this side xk plus 1 is smaller than xk plus 1 xk yk plus 1. One moment. This side xk plus 1, xk plus 1 minus xk, less or equal than yk plus 1 minus xk, yes, which is equal to xk minus xk minus 1. Why? Because in a triangle across a larger angle lies larger side. So it is elementary geometry. And so this means that this process produces a chain of points such that the distances between them do not grow. They progressively decrease. Yeah? It is already fine. And now we have familiar thing. For n in n, define x n of t with piecewise linear trajectory such that x n of k divided by n equals xk. So we interpolate linearly between the points, between these points xk. And then we go to the non-standard universe. And so we have a function xn of t. It is from star n times star 0, 1 to star omega. So it is the motion along this set of star omega, and then you consider n some infinite integer number, and then I take standard part of xn. X of t. One moment. We have to start this sequence from something. Let us start it so that we have x0 in omega, u0 in e. No, better to say tangent space at the point x0 e. Yes, so it is initial vector, and then y1 equals x0 plus 1 over n times u0, and y1 x1 is projection on omega of y1. So this way we get the first 2 points, x0 and x1, and then we can construct this solution. That's it. So what, in fact, what was done? Was it derivation of equation? No, I did not derive it from anything. I postulated it. Yes, I postulated it works in regular situations. Why it works? No, let us see how it works. Yes, we don't have a better proposal for these such non-smooth situations. So let us consider example. Omega is just segment 0, 1. So if you take x0, u0, then you have x1, and because as long as we can move along this line, they will be at the same distance, because each next point y, k plus 1, if it is on this line, it will coincide with x. So here we have some xk, and here we have yk plus 1. It is already beyond this segment, so xk plus 1 here, xk plus 1. Now we have xk plus 1. By the same rule, we have here, say, y, k plus 2, and again, x, if you take the closest point, it is the point 1, xk plus 2. Yeah? So xk plus 1 is at the point 1, xk plus 2 at the same point 1. So all the further points will be at the same point. Equals xk plus 3. So our discrete approximation shows that the particle moves with constant speed along this segment until it reaches the point 1. And at that point it stops. Yeah, so this definition implies that there is no bouncing. There exist still other model which is much other system which is described by the motion along motion on a convex set. It is the motion of ideal inextensible thread. So what is a thread? Thread is, here is a thread, it is just a curve, no, say in the plane or in three-dimensional space, in any space dimension, maybe even in one-dimensional, which is defined by equation x of s and depending on t. So, for example, s is between 0 and 1, so it is just piece of thread. T is time, so it all depends on time. Yeah? Now, what does mean inextensible? Inextensible means that x of s1t minus x of s2t distance less or equal than model s1 minus s2. Yeah, so if here x of s1t, here x of s2t, yeah, so this is the distance between them in the space, and this is the distance along the thread. Yeah. So this is inextensible thread, and element is proportional to the length of a mass of any piece of this thread is proportional to the length of this piece. So this is the system. Here we have an origin of some paradoxes and misunderstandings. The thread is inextensible, but nobody says that it is incompressible. Yeah? So just imagine that we took this thread and made it like this. And these small wiggles can be infinitesimally small. Yes? So we can compress this thread, we can even compress all this thread in one point. The thread is soft, so it is possible. Yeah, so, but it cannot be extended. So the thread, inextensible thread, is something which is opposite to incompressible fluid. Fluid is incompressible if each volume of this fluid can be compressed. But again, it cannot be compressed, but it cannot be expanded. So the fluid can be formed in a form of infinitesimally small drops, or like a foam, a fluid with infinitesimal bubbles in it. Yeah? So the fluid can be expanded, and thread can be compressed. So from this we see that the thread and the fluid are sort of opposite in their properties. Yes? And if for the thread we can formulate a good theory, at least propose a model, this means that for the fluid it is much trickier. because fluid is opposite to thread. Okay, so but now how to formulate what is our set omega? Set of x from 0, 1 to our space, say, R nu, such that for any x, for any S1, for any S1 in 0, 1, for any S2 in 0, 1, you have the following. X of S1 minus X of S2 less or equal than modular S1 minus S2. This is a set. So from this we see that these maps are continuous, bounded, and important that omega is convex. So if you have two such configurations, then the convex combination is also in this set. Yes, no, okay, let us write. We have x and we have y. 0, 1 into R nu. And now let us take z of s equals a x of s plus 1 minus a y of s. Yeah. A is between 0 and 1. So this is a convex combination of x, s, and y, s. And now let us find modular z of s1 minus z of s2 equals modular a x of s1 plus 1 minus a s2 a x of s1 plus 1 minus a y of s1 minus a s of x2 plus 1 minus a s x of s2 y of s2. This equals, okay, it is equals a times x of s1 minus x of s2 plus 1 minus a times y of s1 minus y of s2 and this is less or equal A modulo S1 minus S1 minus S2 plus 1 minus A modulo S1 minus S2, which is equal modulo S1 minus S2. Yeah. So if you start Z S1 minus Z S2 less than S1 minus S2. So this is a convex set. And now we can we can construct in the way we consider reasonable motion of the thread. Now, to have something which we can see some concrete example, let me add some other condition. Let us consider the motion of the thread in one dimension. Yes? So the thread can move on the line of this or this way. And as I say, it can expand, it cannot expand, but it can shrink. So we have a lot of possible motions. And we impose one more condition, namely x of s more equal than 0. So it looks like this. We have a motion of a thread. No, the thread can have these pieces like this. It is moving in the vertical, along the vertical line in the upper semi-place, semi-space. Yeah. Moment. Here is the thread. So this is this thread, and now it is moving in the vertical. So if I drop it, it will fall down on the table. So how it will move? I think he will move down. Okay, but yes, so it moves down and doesn't bounce up. Yeah, so it moves perfectly like that material point, which can move inside the segment, and when it reaches end point, it stops. So this thread really moves the same way. Yeah, no, the chain is the best model of a thread. So if you repeat this experiment as many times as you wish, you have always the same result. So this means that here we have some phenomenon which should be described somehow. Yeah. So again, what happens when it falls this way on the table? If I have time for this. Okay, I have exactly the time. So we can we can draw the graphs of this function. So this is s, and this is x of s. And initially, this function s from 0 to 1, it was, say, like this. So this means that the thread is touching initially with its lower end the table, and it is straight. By the way, I have discussed with different specialists, is it possible to take a thread and very accurately put it on the table, will it stay up like a stick? It may be not stable, but is it equilibrium, or it is not? So our model shows that it is not an equilibrium, it will immediately shrink. But does it follow from the model? Okay, it follows from the model, but is it so in reality? I also performed some computer simulations, and it also confirmed that maybe it is an equilibrium, but if you have, say, a chain of 100 links, then this equilibrium is so fragile that practically immediately it falls down freely. So I think that my model is more or less realistic here. No, okay. And now suppose that initial velocity is -1. So our system is moving down. I don't want to include gravity, so just we pushed all this thread vertically down. So what will happen next? Next will happen that at the moment delta t, or t equal 1 over n, it is x0. This is x1 of s. Yeah? Part of this thread will be under the surface. Yeah? So we have to find the closest position in this domain omega. It is here. Yeah. Now, what happens next? Next happens that here, yes, we have two positions. Now here it moves down, and here velocity is here this difference is this, so it will assume this shape. Yes, and the closest position will be this. Yeah. Closest admissible, so this is x2 of s. Yeah? Now, similarly, we can follow it step by step and see that x3 will be like this, x4 like this, and so on. So our model yields this solution that this system behaves this way, exactly as we observe it. Yeah? So our experiment and theoretical model give the same results. Congratulations. Yes. Unfortunately, as I said, the thread is not a model of a fluid, by the reason that it is opposite to the fluid. Yes? Its properties are opposite. If here for the thread, the domain or the set omega is convex, for the fluid it is, no, I would say everywhere concave. Yeah?
So it is concave.
Yeah, concave everywhere. Yes, it is a terrible thing. And so for the systems like fluid or a little, no, maybe just a step one step closer to the fluids. We need other principles which describe them, and which also can be formulated in non-standard language, and I will do it next time. So it is not finish of dynamics, it's just beginning of dynamics. So let's finish today.